webinar series with Francis Bach from INRIA. Great pleasure that Francis agreed to speak, and this is one of the special virtues of our virtual times, that we can have speakers like Francis participate pretty easily. And most people in machine learning are well aware of Francis's achievements. He's been a researcher at INRIA since 2011, doing work at the intersection of machine learning and optimization. And you can look at his remarkable bio, but he has been a forerunner and early creator of many cool ideas in the world of machine learning, including during his PhD that he got in UC Berkeley in 2005, Mike Jordan's group. And Francis has worked on a variety of things relating to kernel methods. He's master of duality in optimization, and he's also worked in continuous submodular optimization and a variety. He's been part of many very influential works. One of the more recent ones which triggered a huge development in the world of stochastic optimization was also the work for which he co-received the Lagrange Prize in continuous optimization related to stochastic gradient methods and so on. And he has been chair of ICML, and he's also co-editor of the flagship journal of machine learning, which is JMLR. And I would encourage you to have a look at the great amount of prolific work that Francis's group produces. And I think I don't want to eat too much into your time, Francis, and I will hand over the controls to you just in a minute. I'll just tell everybody that to kind of counter Zoom bombing, everybody's fully muted. If anybody wants to ask a question, please use the raise your hand feature of Zoom, and I will try to monitor that and unmute you so that you can ask a question. And Francis said that he has good pause points during the talk where the audience will have a chance to ask questions. And let's try to have the meeting as interactive as possible. And it may take an instant, until I've seen you raise hand and unmuted, etc. But by now, I think all of us are fairly comfortable with Zoom. So I think with that, Francis, welcome, and now you can zoom ahead.
Okay, so thank you, Sorit, for the invitation and for the very generous introduction. So today I'm going to talk about joint work with mostly former postdoc Kevin Scaman and Adrian Hendricks, a current student. And really they are the two persons behind most of what I'm going to present today, which is also joint work with Laurent Massouli at INRIA, Sebastian Bubeck at MSA, and Neil Tatley at MSA and the University of Washington. So to give you quickly some context, so we all want to deal with data and in all domains, industry, in all sciences, and there has been a lot of different types of hypes, and at the moment people use a lot machine learning and obtain some somewhat intelligent behavior, of course intelligence in quotes, and which is a combination of specific models, new algorithms, a lot of data, and of course some computing power. And today I want to touch upon one issue, which is the the interaction between algorithms and computing power. The idea being that since Moore's law has more or less ended, so if you want to get more power, you cannot simply buy a bigger computer. You have to buy more machines or more processors per machine. So essentially you have to start to do machine learning over multiple machines. And this is the topic of today, machine learning over networks. Okay, so here I'm going to use networks quite in the broad sense. So this includes really a network, machines in different places, but also you can imagine a multi-core or data center or a multi-core machine as being also processors of our network. So there'll be three parts of my presentation. The first part will be machine learning, okay, no distribution, just optimization for machine learning. Second part will be distributed optimization without machine learning. Okay, so how you optimize a function which is defined over a network. And finally, the last part will be combining the two. Hopefully you get the best of both worlds. All right, so just to give some setup. So I'm going to observe observations, xi, yi. Xi can be an image, yi can be a label on that image, and I observe n of them, and typically quite big. And I want to predict y given x, like a classical prediction function, h of x and theta. And theta will be the parameter I'm optimizing over, typically in d dimensions, and d will be also quite large. So first classical model, linear models, okay, where you are linear in the parameter theta and maybe nonlinear in the x through some feature function phi of x. And it is still used quite a bit with both n and d being very large. And most of what I'm going to talk about today will apply to that case because I'm going to assume convexity, and I'll come back to that in a few slides. But clearly, one of the goals is to go beyond those linear models. And if you want to do computer vision, okay, like discriminating between cats and dogs, then people now use neural networks, which are combinations of linear models and non-linearity. And those non-linearity sigma here makes it harder for optimization. But again, I'm going to focus mostly on the linear models. All right, so the way those problems are cast is through an optimization problem where I'm going to minimize the regularized empirical risk, where I'm going to average over my training data the average of like a loss function between yi, my label, and my prediction function, and plus some regularizer to avoid overfitting. So in this talk, if you wish, you can think of the loss as being least squares, or if you don't like least squares, which is a bad idea, you can do logistic as well. Okay, so I'm going to assume that the loss is convex, and this is like a somewhat weak assumption. So now go back to this like general framework. Then just as a side note, this is not the goal of machine learning. Okay, the goal of learning is to do well on unseen data, but I'm going to ignore it totally in this talk. Okay, just a reminder, learning is more than optimization. But today I'm going to focus on the optimization aspect. And what is particular about optimization for us is that we are minimizing a finite sum, okay, some average of the training data of some functions. Okay, so this is really the core topic of the talk. How are we going to minimize those finite sums? So here, last slide about that, I'm going to go convex, so assuming linear models essentially for H. All right, so this is the classical finite sum. So there are two classes of algorithms, the so-called batch gradient techniques, where you go down the negative gradient of your finite sum. And so it's known that the convergence rate in the strongly convex case is dictated by the condition number, kappa. So here, kappa is the condition number, so the ratio between the largest and smallest eigenvalues of the Hessians. And this is like very classical. And for machine learning, you can imagine kappa here is n, typically, because people tend to regularize in high dimensions. The condition number ends up being of the order of n. So whenever you see kappa, you could imagine kappa is n. So this can be accelerated using like a Nesterov acceleration, but you still get you get square root kappa, which is quite a strong gain. But the problem is that it's fast in terms of number of iterations, but every iteration takes O of nd, like computing n gradients in dimension d. So when n and d are very large, this is very costly. The opposite, you have SGD, which is like the where you take a single function at every time step. So I of t here is selected at random. And so by design, every iteration has a small cost. So it's independent of n, but you lose exponential behavior and you go back to this kappa over t. Okay, so this is like you do a lot of cheap iterations. So in the last 10 years, people have looked at improved ways of doing optimization of finite sum. And this started with Nicolas Leroux, Mark Schmidt, and I in 2012, and then important contribution of Johnson and Zheng and colleagues, and of many others afterwards. And the idea is to start from this stochastic gradient descent over there and notice that this update, so this gradient, this stochastic gradient, if you take the expectation with respect to I of t, you get back the full average. Okay, so it's called an unbiased gradient estimation, and this unbiasedness is good for convergence, but since you still have some variance which is not vanishing, then you cannot use like a constant step size, and you have to, in a sense, like reduce the variance by having smaller step sizes. And what those methods are doing, either explicitly or implicitly, is to reduce the variance of this gradient estimate by simply removing like a random variable, okay, and adding back its average with respect to I. So this is still unbiased if you take the expectation with respect to I of t. But if you choose as vector z, like things which are quite correlated with the gradients, then you're going to reduce variance, which is a classical technique in Markov chain Monte Carlo. And it turns out that by storing past gradients, you can indeed reduce this variance. So not only like by hoping it's going to reduce the variance, but you can probably reduce the variance. So just as a side note, this is really highlighted by the nice paper by SVRG. All right, so this is just to give you a highlight of how things are working. And this is still like one line of
Okay, Francis, can you hear me? Signal seems to have broken. Let's wait a moment, maybe comes back on. Okay, probably Francis has to reconnect. This is the kind of trade-off between having a pre-recorded versus live talk. Sometimes this can happen. Maybe we can.
back again. Aha. Okay, so sorry about this interruption. Is it all fine? Can you, okay? Okay, good. All right, so yeah, sorry about that. So I was saying that you can replace the product of n times condition number, which can be quite large when kappa is of order n, by a sum between n and condition number. Okay, so this is like a bit like simplification of what's happening actually, but it's just like a good way of saying it. And you can do acceleration, okay, and you can replace this n plus kappa by n plus square root of n kappa. So for problems which are very difficult, where the condition number is larger than n, then this helps. And in a very nice way, you get matching upper and lower bounds of complexity. So if you want to optimize finite sums, then you cannot do better than those algorithms, okay, that LAN and others have designed. Right, so now let me go over, like I was not doing any distribution. Let's now go over a bit distribution, okay? So we are now, the goal is also to minimize some finite sum, but it's a kind of a different finite sum, okay? So but before we had a finite sum because we had like an average, okay, over data points. And here we have, want to minimize some function h, okay? And each of them is a gi, okay? Each element of the finite sum is gi, and the idea here is that gi can only be accessed by a certain node I in the graph. And just to make things like clear, typically for machine learning, gi of theta is the average error of the data set, which is like located in node I. So essentially, the finite sum from 2 slides ago are essentially each element of the finite sum. So each gi is a finite sum. Okay, so this is I will try to make notations clear like this. So I have a big finite sum, okay? And for the moment, I'm going to ignore the fact that the GIs are finite sums. I just have finite sums. I have functions which are defined over a network, and I want to optimize them as well as I can, ignoring the fact that each of them is a finite sum. All right, so why is it relevant to only have this this setup in a graph? So the idea is that each function can access its own, each node can access its own functions and gradients, and can communicate like gradients to neighboring nodes. Okay, so this is an idealization of distributed computing. So clearly we're ignoring a lot of what's happening under the hood. So we are not counting bits, we are simply exchanging gradients or vectors among neighbors. So this is can be done at several like levels. It can be like each node here can be like a place in the world, okay, or it can be like a place in your data center, or can be like a location in your own server, okay. And the idea is that you want to do distribution to leverage the power of multiple nodes. This is typically one reason, also because you're not allowed to share data. So this is like very classical. If you have medical data, you're not allowed to share, to store the data at the same place. Okay, and the goal now is not only to minimize local computation, which was a goal like earlier. The goal is also to minimize communication. Because the idea being that if your machines are far apart, you don't want to pay or to wait too long by. You don't want to have a good example. Okay, so my network was shut down, so you want to avoid like problems because of network issues. All right, so the first solution is simply why not take the best you can do for minimizing some function h and trying to make it and to distribute it through the network. Okay, so this is the best you can do, like for like context optimization, like Nesterov accelerated gradient, and just go down the negative gradient, and you notice immediately that you know that the number of iterations that you need is depend on the condition number, like square root kappa times log of 1 over epsilon. But you have to compute gradients. And now the idea is, how can I compute gradients over the network? So I've replaced the core sub routine has to be network averaging. And this is what I'm going to describe now. So I have like m nodes, and I want to average m numbers. So you can see each of those numbers as being one component of one gradient. Okay, so I want to average to get the full gradient. And the average is just the average can be the minimizer of like this simple cost function. So this is an instance in itself of minimizing a finite sum. There are two types of algorithms in that setup. You have the so-called centralized algorithm, where you have one node can declare itself the leader, and then all the others will follow. And the idea here is that you can really do the averaging in a minimal amount of time because you synchronize everything. And there is, so the leader will first, like typically the easiest one is to build like a spanning tree about the graph. Okay, so this, you can lose a factor of 2 in the diameter in the graph. And then you declare a node, the leader, let's say node 4. And whenever you need to access, to compute the full gradient, you ask all of the nodes to send their gradients, and you accumulate the sums while going to the root node, to the leader node. And this can be done in a number of time steps, which is the diameter of the graph. And then if you need to send the parameter values back, you simply like send the parameter values also. If you do things in parallel, only number of diameter, but the time it takes is diameter. Okay. So here, clearly what's important is that when I say it takes time diameter, is because I'm allowed when things are communicating, when 2 communicates to 4, this can be done at the same time as 6 communicating to 4. Okay, so the total amount of communication will be larger, but in terms of time, it will be parallel. All right, so this is all very nice. And what we showed with Kevin Scammer and Sebastian Lübeck, Itatli, and Laurent Massoulier is that you cannot beat that, in the sense that you cannot avoid having those many gradient steps. And this is normal because this is simply like, even with a single machine, this is what the best you can do. But we should as well that those number of communication steps were also optimal. Okay, so in a sense, if you're centralized and you want to do optimization, the simplest possible algorithm which is simply distributing Nesterov accelerated gradient is enough. Question is, this may be not very robust, because if your one node gets down, like for us today, I was a leader, my node got, my Wi-Fi got canceled, but got shut down and everything was stopped. Similar here, you would like robustness because of network failures in particular. So
also, there's a question. I think Philippe has a question.
Yeah, go ahead.
Yeah, when you say optimal, you mean that it's optimal for any graph, or you can find a graph for which it's optimal?
Oh la la, that's a tough question. I think for
this was an outstanding presentation and results. If I'm sorry, I'm kidding. Go ahead.
I think that's. I think for this one, if you give me a graph, I will give you a set of functions on which you cannot beat that. Okay. If you go in the centralized setup, then it's not the case. So the Lebrun will be, I'm giving the graph, I'm giving the bad graph. Now here, I think because you take a graph, you take a spanning tree, and then you organize things in the spanning tree. So I think for the centralized setup, I think it's okay. You give me the graph and I give you the functions. I think so. I think this is what's happening.
Okay, thanks.
All right. Okay, so then people want to go decentralized to avoid those robustness issues, and often people use what is termed gossip. And the idea is that you're going to communicate with your neighbors, and you're going to replace the current value by the average of all your neighbors. So every time you do gossip, a node wakes up and asks for the neighboring nodes, and this corresponds to replacing the value theta I by the average of the values at your neighbors. So here Wij will be 0 if Ij are not neighbors, and different from 0 if you are a neighbor. All right, so the idea is to be, you can be potentially asynchronous. Okay, so the node 4 may wake up at a different time as node 7. Okay, and the network may even change, although we are not considering this at this time. Okay, so even simpler for the first part of the talk, we consider synchronous gossip, which is a situation where all nodes wake up at the same time. Okay, so since you're doing all of those operations at the same time, since you replace the vector of parameter theta by just the value at the previous time times the matrix W. So this means that after t steps, you get the matrix power, and since you initialize with the current values, this is the exact formula. Okay, so this is really a very simple, ideal way of doing communication, and which essentially amounts to do a matrix multiplication. And to make my life even simpler, I'm going to assume W is symmetric and W is stochastic, and the stochastic being that if you're constant, you don't want to move. Okay, so constants have to be preserved. And this is like typical assumption that people make in this area. All right, so how does it converge? So it's well known, okay? So you have a linear dynamical system. This will depend on the largest eigenvalue of W, and in particular on the gap, the gap between the first lambda1 and the second lambda2 eigenvalue of W. And because I'm assuming W stochastic, the first eigenvalue is 1, and I get hence, I get like a gap, and this gap, the inverse of this gap is often called the mixing time of the associated Markov chain. The idea being that when you gossip about the graph, after this mixing time, you have shared your value with everybody. Okay, it's a classical concept in Markov chain theory, and it's not surprising that to achieve precision 1 epsilon for network averaging, you need a time which is proportional to the mixing time. So of course, you need mixing times the log of 1 over epsilon to achieve a high precision, but really the mixing time plays the role of the condition number for optimization. And not surprisingly, all the bounds I'm going to show now will have a part which is for optimization, condition number, and a part which is for distribution and message passing, which is like mixing time. So let's look how it works. So I have a nice video. It's mostly to show how it does not work. So here I'm launching gossip. So I have like 100 nodes on the 2D grid, and I'm launching gossip with a basic like connecting to my direct neighbors. And as you can see, so I'm starting, Okay, I'm starting with like positive node there, negative node there, and I'm supposed to converge to all the same nodes because gossip, at the end of gossip, everybody has converged to the same value. And as you can see, you need a lot of steps before you get to something which is close to uniform. Okay? So this is just to highlight the fact that gossip is very slow. So everything is done in parallel, but here the mixing time on the 2 degrees is really bad, and it takes a while. Okay? So this is just to highlight the fact that it's still quite slow, and highlight the fact that I'm going to accelerate it later. All right, so now let's try to mix gossip and optimization. So this has been done by already like many people, in particular Angela Nedick and Asu Asdagla with an important paper in 2009, and then by a series of other people, and mostly for convex problems. And so I'm going to present simply one version of that today. All right, so first some lower bounds. So this is joint work with Kevin and the other colleagues I've mentioned earlier. And what we showed is that the best lower bound would be the classical lower bound for Nesterov acceleration. And now a lower bound, which is similar as the one from before, where you replace diameter by the square root of the mixing time. Okay, so here, going back to Philip's question, it's not as strong a lower bound as we had before because I think we construct a bad graph instead of relying on a given graph. And the first element is that if you do plain gossip, so if you try to simply replace the centralized averaging by this decentralized averaging, then you're not optimal. The reason being that as you go along in your optimize, you need to have higher and higher precisions to do gossiping, and then you need to do more and more gossiping. And because it's hard to once start the gossiping that's set up, you cannot really, you have an issue about like, you have to gossip too much. And the question is, since we have a lower bound and the simplest algorithm is not achieving the lower bound, can you do better? Okay, can you do that? Can you make the two bounds like a match? So for this, we have to go to the dual. Okay, so I hope I can be the master of duality that Suvrit was describing me as. And so this is finite sum. I'm going to dual online. So it could be the only technical slide of today. So this is using a nice formulation by Jakovetic and colleague. So we have a finite sum like this. So we're going to first duplicate our parameter vectors. So theta I will be the version of the parameter theta as node I. And of course, if you want to make sure that the two problems are equivalent, you simply need to add some constraints that along the edges of the graph, then the two versions are equal. So if your graph is connected, this is equivalent. Then, since you see, you introduce one Lagrange multipliers per constraint. Okay, so lambda ij is a vector in size D, and you have as many as you have edges. And then you just sweep min and max, and you realize that because I've introduced Lagrange multipliers, this is like separable in I, and the linear function also is separable in I. So you end up with a problem which is a max of sums of function of I. Okay, of a function of lambda. So lambda is a big set of all Lagrange multipliers, and you have a sum of functions. And even more, each function I will only involve like lambdas, which are neighbors in the graph. All right, so now we have a dual problem, and it turns out that if you take that dual problem and do the simplest possible algorithm that you could think of, which is accelerated gradient descent, then you can show that the steps that you need to do this acceleration are exactly equivalent to do one gradient step and one gossip step. Okay, so this is like what we did with Kevin. And even better, if you do that, you can compute convergence rates without the need to invent anything. You just reuse the convergence proofs from Nesterov, and then you obtain some like classic number of gradient steps and some number of communication steps. Okay, and if you do this, you realize that you're not optimal. Okay, so the reason being that the gossip is too small. So we need too slow. So we need to accelerate gossip, and this is what we have used with my colleagues, Kevin and colleagues.
Francis, quick question.
Yeah, go ahead.
The rate that you mentioned, that is for achieving primal suboptimality?
Oh, that's to achieve dual suboptimality, but because I'm strongly convex and smooth, it's the same.
Mm-hmm.
Okay. So here, that's a good point. So here also small caveat. That when I say local granular computations, at least in that version, I need to know the function dual of GI, okay, which is a bit annoying, but we have ways. So if you have a composite term, it's okay. But yeah, so here, since this is to me not a final answer, I'm going to focus more on the next algorithm. So we need acceleration. So we are using like classical techniques from linear algebra. So whenever you have like matrix powers like applied to a vector, then there are ways of accelerating it. And this was done by, I think, Aioli and Scott in the context of gossip, and also quite similar to the so-called shift register gossip by Kao and colleagues. And the idea is to combine iterates linearly like this. So I'm going to not only use the last theta k, but all of the theta k's and averaging them with some weights alpha k. And because theta k is a matrix power like this, I get a polynomial in W times the initial vector C. And now you see me coming. I'm going to optimize over the polynomials. And not surprisingly, the optimal polynomial is a Chebyshev polynomial, and which is giving you a right. But even better, you can compute the Chebyshev polynomial recursively without the need of storing all iterates. This is like textbook Chebyshev acceleration, which you can apply to the problem. Okay, and now, like conjugate gradient, Chebyshev will replace the condition number of the problem, which is mixing time, by the square root of this mixing time. And now it starts to be faster. And let's look in my 2D problem. So on the left, before acceleration, on the right, after acceleration. As you can see, after like 40 steps here, you're already reasonably uniform, whereas you're still struggling with regular gossip. Okay, so this is just a video to highlight the fact that there's a strong difference between before acceleration and after acceleration and before acceleration. All right, so now we can combine with gossip with the optimization, and now you get to optimality. You get optimal complexity for optimization. Okay, so this
Francis, can I ask a quick question?
Of course, sure. Go ahead, Mert.
Sure. So this sounds a bit like the over-relaxation techniques in linear algebra, and
it is. I think often if you take the book, in the book by Golub and Van Loon, Chebyshev acceleration is presented as a relaxation technique. Yeah. It is. Okay. It is. But it's simply since you have to choose the omegas like in the Chebyshev, like so Chebyshev recursion is often called Chebyshev acceleration.
Exactly. But do you need to know about the graph? Do you need to know about the graph to choose those parameters a bit, or you are independent of the graph to?
Oh no. Okay. So here you have to know the gamma.
Okay. So I see. And then that can probably be estimated in a distributed fashion anyways, probably.
Oh, you could, but I have to admit, we didn't really care about like those details, but they are important in practice. And I think in the simulation that we are doing, I think we need a spectral graph for sure.
Okay, thank you.
Yeah. So any other questions on the optimization without any machine learning at the moment? Okay. So now let me go to the last part of the talk when I'm going to, so I've done learning when I say it's optimal behavior. I've done like optimization of our networks, optimal behavior. Let's try to combine them. Okay, so I'm going to go back to this consensus problem. Okay, you minimize the finite sum. And now I'm going to leverage the fact that every GI is also a finite sum. And Ni here, the number of nodes, number of data points per machine will be the uniform N, and N will be quite large. So what we have seen so far, we have two solutions for this. Either we put everything in a single machine. So if I have n machines with n data points each, I can put in a single machine and get nm total data points. And I can use like accelerated saga or whatever accelerated algorithm that I have, and I will pay that price, number of data points times the square root of number of data points times condition number. I will pay zero cost in communication if I ignore the communication it takes to put everything in a single machine. Whereas if I do MSDA, so MSDA is the algorithm from before, then looking at the rates that we had, we're going to do some gradient steps, and every gradient step will be proportional to n, because every time I need to compute a gradient of GI, I have to average over all gradients. So same issue as with a batch gradient descent, I'm going to pay a cost of n, okay? And if you look, a cost of n, and then I'm going to communicate so. And as you can see, as soon as I go from 1 to 2 machines, okay, if m is equal to 2, okay, because I'm using a different algorithm, I cannot use a finite sum setup. So I'm losing a lot because I'm not using the good algorithm that is leveraging the finite sum. So in a sense, if you start to use this for machine learning, it's optimal for all GIs, but not optimal at all for a finite sum. Okay, so this is really a problem. And second, it's only synchronous, but I don't want to talk about that. So let's now look how you can like do everything at the same time. And this is joint work with Adrien Hendricks and Laurent Massoulier from last year. And really now we are focusing on a very particular problem, which is like linear predictions. Okay, we can allow for partial asynchrony. So when I mean partial, we need to have a common clock. So as soon as we have some common clock, then things can be done asynchronously, but sometimes some operations have to be done at the same time. And what we were able to show is to get this algorithm ADFS, which is achieving some complexity, which is this one. And the key here is to realize the fact that if n equals 1, okay, one machine, you get back to what we had before for a single machine. Okay, and this is really what is important to us. And also, if you have a single node per machine, if n is 1, you recover also MSDA. So it does extend the two algorithms. So how does it work? It's very simple. And in fact, it's very simple. Yeah. In principle, the idea is to create some equivalent graph. It's a very nice idea by Adrien Hendricks, is that you take your sum of sums. Okay, so you have a sum I goes over machines, and the index j goes over like data points in your machine. So you end up with a huge finite sum like that. And the way, and this is, you start with a network over there with, you have 3 machines, and you need to create some equivalent graph, which will have all functions. Okay, so each, it should be G here, sorry, it should be G1. Yeah, I'm sorry, I changed notation. It should be G1. This is your function at this node. Okay, it's a big sum like that. So I'm going to create a new graph. Okay, so here, if I have 3 data points, I'm going to add is the actual node, the regularizer, and add fake nodes, which are my data points. Okay, so if I start with like 3 edges over there, I end up with like 3 edges plus as many edges as I have data points. And now we have like a graph like this, which each node has a function, and we can apply the exact same framework as before. So go to the dual, okay, and now replace accelerated gradient descent by randomized coordinate descent or coordinate ascent, and this allows to do the trick. Okay, so this is the only this is the way we're going to do it. So of course there is a lot of computations behind the scenes to make sure that the rates are correct and so on. So if you want to know more, you can look at the paper. But I think the idea is really to create an equivalent graph, which is here. So again, it should be G1 over there, and G3 and G2. Okay, and once you add that, just you get the new graph, and you just run the classical algorithm. So how does it work? So we can look at running time of some actual cluster, so the one in the lab, and so we try like on a basic problem, and n equals m is the number of machines, like small number of machines on the left, larger number of machines on the right, and we compare to the blue. Blue is us, and green is the single machine algorithm, and this is all the other competing the baselines for distributed optimization. So as you can see, if you take a small number of machines, then it doesn't add, it doesn't like, you don't gain much in having like more machines. You don't do worse, but you don't gain that much. Okay, this is classical. Before you see the benefits, it takes a bit of time. But the key here is that all the other competing algorithms with a small number of machines, they do really bad. Whereas now, if you take with a bigger number of machines, then a single machine optimization in green starts to be very slow, while ours remain the same. Okay, so this is just confirming the result that we have shown earlier. We can even do a bit better and comparing like baselines with what we have. And again, so the rates that we see in our bounds, you can also exhibit them in practice. This is most variance reduction technique happens to satisfy that property that you see the linear behavior in a semi-log plot. All right. And yeah, so to conclude on this, so I've tried to present distributed, decentralized machine learning algorithms. And the idea here, okay, if you remember a single thing, is that when you do parallel processing, you need to compare yourself to the best algorithm for a single machine, okay? And not for your own algorithm with one machine, which is a standard thing that people do. If you start by taking a slow algorithm in one machine, a slow and a robust algorithm, it's easy because take a slow one, which is robust to everything, and you can get linear speedups on that. So linear speedups mean that you are n times faster if you have m machines. But since it's n times faster than something that could be very slow, you don't gain at the end. So the idea in this work is to look at, to try to make parallel the best possible algorithms. Okay, and so here the best on a single machine is variance reduction, accelerated variance reduction. Sorry, and what we obtain if you have n machines and m observations is that you go to this complexity to that complexity. So at least if kappa is not too large, you replace nm by m. So you exhibit sometimes linear speedups. And if you have a very hard problem, you only exhibit a square root speedup. Okay, so this is the current thing that we can propose. So a few extensions. So first, what we have at the moment is not a primal algorithm, okay, in the sense that we have to go to dual and use a dual formulation. And so we do dual coordinate asset essentially. And this, I don't like it so much because it requires some oracles on the dual function, okay, which is a bit sometimes annoying. And we have spent some time trying to find a primal only algorithm. First, because I think it's easier to implement because there is no don't go to dual. And second, it becomes a good candidate for going non-convex. Okay, so typically the first step towards allowing yourself to think about non-convex is to do like a primal only algorithm. And this is what we have achieved to this recently accepted NIRI's paper with also Adrien Hendricks and Laurent Massoulier, achieving like similar bounds. Then is there a lower bound? Okay, so in the context when n equals 1 with a single, no, oh, sorry, this is like n and m are inverted there. Okay, sorry. I've changed notations like during the slides, and now this is abstract. So this should be, yes, so n this slide is correct. Okay, sorry about that. No, I'm lost. Yeah, so when m is 1, so if you have one function per machine, then we know that what we have presented is optimal. Like, of course, optimal in the sense that that I've not defined properly, but in the Nesterov sense. And now, question is, do you have a matching complexity bound for those problems? Okay, if I have finite sum of finite sums, and it turns out that also Adrien has been very productive during like lockdown and was able to also prove some lower bounds. Good, so this is like partly down, but now there is like others which are, I think, a bit harder. The first one is full asynchrony. Actually, we want things to be behaving like totally in the asynchronous way without any like common clock. And this one is difficult. And we don't have like a strong solution yet. And the reason for difficulty is for acceleration. With acceleration, you need to do some linear extrapolation steps, which have to be global. And so if there's no common clock, it's very hard to do. Of course, going beyond convex problems. Okay, so this is of course, very important in practice for reasons that you may imagine. And also trying to go beyond our own cluster, doing experiments on large scale clouds, but we are not there yet. Okay. So thank you for your attention.
Thank you, Francis, for your talk. And now the floor is open for questions, or whatever, the room is open for questions. So go ahead and anybody, and I have enabled you to unmute yourself. So anybody who wants to ask a question can unmute themselves and ask a question directly.
This will be anarchy now. Good.
Let's see.
Maybe I could ask a quick question to Francis.
Go ahead, Matt.
Thanks. So for weakly convex setting, I sometimes see some rates about gradient methods. Do you think there is some hope to get some distributed rates for weakly convex functions?
Oh, no,
weakly convex in the sense that it's non-convex, not the merely convex, but it's the weakly convex setting, which is a non-convex setting.
What is weakly convex? So I know convex.
Sure. So weakly convex is like you add some constant times x squared to your function.
Oh, okay, that's fine. Oh, okay, that's for weak convexity. So it's not convex. Okay. No, but as soon as you enter the world of non-convex functions, then you're going to lose global rates. So you may do the classical non-convex trick to get like the average square gradient. But what I don't like in those analyses is that it's often the average, the random, the expectation of a random, it's average of square gradients over your trajectory. Just weak. I don't know how you can do better than that, but clearly, when I say beyond convex problems, yes, the low-hanging fruit is to do this, to find a way to go from distance to optimum in function values to average gradient. And having a primal algorithm from Adrien is a one step toward that. We have not done it, but it's to me, it's a necessary step. But no, I'm not an expert.
Acceleration also remains a barrier there.
The
acceleration.
Okay. So here, in the primal case, so the way we do acceleration is a kind of a cheat in the sense that we use accelerated gossip, which is like
that is always
also we do catalyst. I think we do catalyst to get a square root kappa. Okay, and so to me, if you want to go non-convex, acceleration is gone anyway, and I believe the primal algorithm that Adrien has done is super basic in principle. It's using I think a trick by Lin Chao is that if you do coordinate ascent in the dual, we're using not the square Breimann divergence, and use your own function as the Breimann divergence, then you get back a primal algorithm. I think it's a very nice trick by Lin Chao, and which we're using as well. So we do like randomized Breimann coordinate ascent in the dual, which happens to be equivalent to a pure primal algorithm. So it's a very nice trick. So of course, there's a bit more to it in our paper to make it work, but I think really the core idea is from Lin Chao, I think, of doing this.
Interesting.
Thanks very much. Yeah, thank you for the explanation.
Anybody else? Feel free to ask anything you want to ask. Let's see if maybe somebody may be thinking. Francis, can you quickly comment about the second bullet about matching running time complexity lower bounds? Is there any key trick to proving a lower bound?
No, I think I should have mentioned it, but in all the lower bounds that we're proving, in fact, we're relying on the two known lower bounds, okay, that is known for optimization. So take the Nester of ones. So if you know about it, it's a Laplacian on the chain, the lower bound function. And since we have a Laplacian on the chain, it does go well with having a network. And we simply take that function, which is a Laplacian on the chain, to a sum of local functions, and we put it on the graph, and you get a lower bound like this. So this is like reasonably easy for the non-finite sum setup. And for the finite sum setup, we also, I think, read the technique from probably George Land, which is looking at coordinates, like functions which are separable of our coordinates, if I remember correctly. And we combine that on the graph. Okay.
Because this suggests that in the non-convex case, it may be easier to first prove a lower bound than an upper bound.
Yeah, but it's against my principles.
Okay.
I'm joking. That was a joke, but partly a joke. But yeah, so I think I should mention it. I think the proof of the lower bound for the graph are also like using the same techniques as Ohad Shamir had done with somebody else, I forgot, where they prove lower bound for the fully connected case. Okay? So the complete graph, and what we do is any graph. Okay? So this is different as well. So we really rely on existing work that is dealing well with a single node and dealing well with a complete graph, and we combine those together.
I have actually one more question, unless anybody else has, because I have maybe too many questions, so I don't want to take over everything. Maybe I'll give a chance to somebody else to ask before I ask my question.
Can I ask you one quick question? So if I'm understanding correctly, so basically you solve like dual problem, and then accelerated method on the dual corresponds to like alternating like the gradient method and the gossip.
Yep.
And you said like you can modify this gossip with the accelerated gossip just so that you can accelerate. And I was just wondering whether like this modification, how does that correspond to like optimization method on the dual? If my question makes sense.
Okay, so I think the one thing, okay, I'm going to answer a different question, which is, so I don't like modifying the gossip, okay, doing the accelerated gossip. So I'm not a big fan of those catalyst technique. So I like them because they give you rates, but doing like as the inner loop, like having inner loops and outer loops, I don't like it. So by that case, I think I prefer a single loop algorithm. It turns out that here, using this augmented graph, we get some decoupling of data and gossip terms, and we don't need to do like accelerated gossip. The acceleration is done automatically. Okay, so in this one, indeed, we don't need to invoke an extra step. Okay, an extra acceleration by Chebyshev. What we did before, we had to invoke this Chebyshev acceleration, and to me, it mostly means that we were not able to do it correctly from the first place. Okay, so I think it's perfectly fine. I think what we did, I think it's perfectly fine. Gives you the optimal rate. I always prefer like single loop algorithms because they're easier to tune, and yeah. So, but that's. But don't get me wrong. I love catalyst. I would not say. It's just I prefer to avoid it when I can.
Why is the case that you cannot apply like this to the previous case? It's a really dumb question.
Why can you apply this one?
Yeah.
Oh, but the idea that you get a huge finite sum over there, but you need to have a sum over, you need to have as many nodes as you have like functions. So we create the number of nodes, which is the number of functions. So n times m, and you can check that here it's n times m. And we just need to allocate functions to nodes. And then we have to do randomized coordinate ascent, but everything is hidden in this non-uniform sampling. This is where the subtlety is. You have to adjust
I see.
the non-uniform sampling. Everything, there's no hack. Okay, it's simply you have a formula, but this is where the action is, to define the the non-uniform sampling. And this is where the action is, which is like also a nice contribution from Laurent Massoulier, is to compute the running time of the algorithm. Okay, so the running time here, because you have to follow some order, you have the running time is a random variable, and you have to compute the expectation. And I think to do this correctly, from what I remember, this requires some computations over like queuing of like mixing random times on the graph, and this is where also the action is.
Thank you.
Okay, anybody else have any questions? Okay, well, if not, we thank the speaker, and I'll catch Francis offline in the same room after everybody has exited for a few minutes. So thanks everybody, and thanks for attending, and thanks a lot to Francis for agreeing to present this.
Yes, everybody listening, and sorry about the mishap. INRIA shut down its Wi-Fi for 2 minutes. So piece of advice, rely on the cable connection.
Cool. So Francis, what I'm going to do is I'm going to